The strongest magnetic field in the universe could be right here on our Earth. There are places in the universe where matter becomes so wildly distorted that magnetism grows into the unimaginable force known as magnetars. The gravitational compacted cores of these highly dynamic neutron stars concentrate magnetic fields to a strength of around 100 trillion Gauss. Yet there could be zones here on Earth where tiny pockets of magnetism flicker with strength that far exceed even these cosmic monstrosities. An analysis of the particle interactions of the Relativistic Heavy Ion Collider, RHIC, at the U.S. Department of Energy, DOE, Brookhaven National Laboratory, has found traces of record-breaking magnetic fields imprinted on the spray of materials shed by crashing together nuclei of various heavy ions. By measuring the shrapnel of even smaller quark and gluon particles set free by the off-center collisions, physicists have gained insight into the forces at work deep inside the atoms. This is the first measurement of how the magnetic field interacts with the quark-gluon plasma, QGP, says D.U. Shen, a physicist at the Solenoidal Tracker at RHIC STAR collaboration at the DOE. Quarks are fundamental particles that flicker in and out of existence in quantum blizzards, their interactions governed by briefly lived gluon particles that bind the quark and antiquark tempests into the protons and neutrons that make up all atoms. Known just how quarks and antiquarks duck and dive in their short lifetimes, inside nuclear particles helps physicists better understand the construction of matter from the ground up, yet the space at the heart of an atom is no place for the faint-hearted. While it's theoretically possible to map the activity of quarks and their oppositely charged antiquark twins using something known as the chiral magnetic effect, in practice the electromagnetic field within a fog of exposed quarks and gluons is too short-lived to catch sight of, rapidly succumbing to the flow of competitive currents. One situation in which physicists thought a handy magnetic field might be generated was a collision between heavy nuclei not perfectly on center. By clipping one another, the protons within the massive bundles would be sent spiraling in a charged swirl that would result in a powerful eddy of magnetism, so powerful they could deliver more Gauss than a quaking neutron star. Those fast-moving positive charges should generate a very strong magnetic field, predicted to be 10 Gausses, say star physicist Gang Wang. This would make these flashes of magnetism 10,000 times stronger than the most powerful magnetar and 10 quadrillion times stronger than the 100 Gauss of a typical fridge magnet. 10 quadrillion times stronger. The magnetars could churn out their magnetic maelstrom for tens of thousands of years. These proton-induced bursts of magnetism would last a mere 10 millionths of a billionth of a second, making any glimpse of the field itself impossible. Yet its presence would still be felt by the charged quarks let loose by the collision. And by throwing gold nuclei into another at various energies, along with mutual collisions of ruthenium and zirconium, the researchers were able to sift through the remnants, and identify paths taken by particles that signified the magnetic field's presence. And knowing this, they could measure the distribution of particles in a way that provided important details on the quark-gluon plasma's electrical conductivity. We can infer the value of the conductivity from our measurements of the collective motion, says Shen. The extent to which the particles are deflected relates directly to the strength of the electromagnetic field and the conductivity in the QGP, and no one has measured the conductivity of QGP before. The research was published in Physical Review X. This is by Mike McRae on Science Alert. Please leave your comments. Thank you for your support. Kindly support my Patreon account The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.